Now we will discuss further about control systems. Now in the last lecture we discussed about the poles, types of poles, like real distinct poles. So this is how you will separate it into the partial fraction. If you get the transfer function like this, okay, then you will separate it in like this into the partial fractions, and then you will take the inverse Laplace. And if you get the repeated poles, you will do like this, like k1 over s1 s plus p1 whole square plus k2 over s plus p1 plus k3 over s plus p2. It means you have to make two coefficients for this denominator, like s plus p1 square, and then alone s plus p1, okay, and then s plus p2. So when you put this equal to 0, you get one coefficient, you will get k1, okay, and when you put this equal to 0, you will get k3. But how will you get k2? So for this you have to compare the coefficients. So you can compare the coefficients of either s square or s or simple constant. You will get the same answer, okay. So this is here the coefficients of s square were compared. Since there is no term s square here, so it is 0 dot s square, and it is equal to k2 s square from here, okay, and plus k3 s square from here. There is no s square here, so just add these things and equate equal to 0. So you will get here k2. So when you get k1, k2, k3, put this here and then take the inverse Laplace. So inverse Laplace of 1 over s square, it is t into e raised to power minus p1t, and here it is k2 into e raised to power minus p1t, and here it is k3 e raised to power minus p2t. p1, p2 are the generic terms, okay. So example are here, like when p is 5, you will get answer like this, okay. Now the complex conjugate, that is a special case that you will not find in the normal nice book, but it's easy that for the complex conjugate you have to just make the coefficient k2 as conjugate, complex conjugate coefficient k2 conjugate over s plus p2 conjugate. And how the solution you will get like this. The solution, for example, if you have like this s into s square plus 0.2 s plus 1.01, conjugate solutions means that there are no real solutions. You get the under root minus 1 term, okay, you get the term of under root minus 1. This is not possible. So we say that it is equal to your iota, but here we say it is equal to j, because this symbol basically confuses with our current, okay. So we use j in electrical engineering everywhere, okay. And here s plus 0.1 minus j. So what will be the roots? Roots will be s minus into minus 0.1 plus j. So this is basically the root, okay. So conjugate will be 0.1 minus j, that will be its conjugate. So now what is the real part and what is the imaginary part? This is like sigma plus j omega. Here sigma will be 0.1, sorry, minus 0.1. here you can say minus 0.1. this is very important point, okay, minus 0.1. don't make this mistake, because you will make the system unstable if you make it positive. And this is sigma is basically the coefficient of E, okay. If sigma is positive, the system will become unstable, okay, because e raised to bar any positive, its graph would be like this. This is unstable. We want graph like this, stable, okay. We want that the system should approach a finite value. When t approaches to infinity, your system should approach a finite value, a bounded value, or 0. If not 0, you can approach it to some fixed finite term, okay. Are you listening my voice clearly? Okay. So okay, I think you muted your mic, that's good, okay. Okay, now what is important here? This is j omega. What is omega here? Here omega is 1. Omega here is 1, because plus j omega is 1. So here sigma is minus 0.1 and omega is 1. Now this is the your a plus b iota form. I discussed yesterday that you have another form like r theta form. So r is equal to under root a square plus b square, and theta is equal to tan inverse b over a. So that is the polar form. So what is the advantage of polar form? When you want to divide or multiply, you use this form, because when you multiply, you just multiply the magnitude like r1 into r2 and add up these angles theta 1 plus theta 2. And when you want to divide, you just divide r1 over r2 and theta 1 minus theta 2. And when this form is feasible, this for the addition and subtraction, you just add the real parts and like a1 plus a2 and b1 plus b2. Or if you want to subtraction, you just subtract from the real parts like a1 minus a2 and b1 minus b2. So these are the some basic concepts. Let me clear this whiteboard. Okay, so what will be the solution? Like for example, you got k1 0.99 and k2 you got like this, you put this equal to 0, you got k2. And what will be value of k2 conjugate? K2 conjugate will be its conjugate like 0.498 and 3.04 angle, then its k2 conjugate will be 0.498 minus 3.04. okay, the opposite sign. So put it here above, you get 0.99 over s, 0.498 angle 3.04, okay, and minus 3.04, and this is the s plus 0.1 minus j. It is basically s minus into minus 0.1 plus j. okay, that minus basically multiplied inside, and you are looking this term like this, but actually it is s minus into minus 0.1 plus j. So now this is a little bit tricky, you have to understand this thing. If you take the inverse Laplace, this is simple, 0.99, it will be 1 u of t like multiplied plus. Now this term is special, and this term you will see in ahead that how to write this one, like 2, okay, 2 multiplied by this magnitude 0.498 and then e raised to power minus sigma t. What is sigma here? It is minus 0.1. okay, here you can see e raised to power minus 0.1 t. Then cos omega t. What is omega here? Omega is 1, so 1 dot t plus phi. Phi is your 3.04, that one angle 3.04. okay, this is, you have to learn this thing, you have to write this. This is 0.99 plus 2 into 0.498 e raised to power minus sigma t, that is 0.1, this is sigma, minus 0.1 t cos of omega t, that is 1 dot t plus phi 3.04. So this is how you obtain this expression. We will further do some in ahead. Okay, now we are moving to the modeling of mechanical systems. Now in mechanical systems we encounter two types of systems, linear systems and rotational systems. Linear systems, like you have displacement in linear in a line, okay, in a straight line, and you have a force, you have a position like y of t, then y dot is equal to the velocity, and the derivative of velocity is equal to the acceleration, that is d double d2y over dt square. okay, and accordingly on in the rotational side, you have for the force you have the torque, that is in Newton meter torque, and for the theta x, here x or y, here you have theta, that is the position is in radians, and its derivative, the derivative of the position would be the angular velocity omega t, and the derivative of the angular velocity will be angular acceleration, that is alpha. okay, that is alpha. So here you have the mass spring system, like there is spring and there is force and there is displacement. So but there is a Hooke's law we have studied in the intermediate, that is Hooke's law. Hooke's law is f of t is equal to k into y of t, that if you apply the force, there will be some increase in the distance, and that is directly proportional. You apply force, you get the proportional displacement. So there is linear relationship. We say that f is directly proportional to y of t, or f is equal to k of t, or k of y. Y of t means y is here it is modeled as y. In the notes there are some symbols which are used differently from the book, from the Norman S. Nice books. So there will be some different, like Norman S. Nice uses this as x, okay, but it has used as y. So both are correct. If you can give any symbol which must be according to your understanding, you should solve the question accordingly. okay, if you use x, you should solve the question according to x. If you use y, you should solve question according to y. Normally y is used for the output of a system. okay, So but here it is used as a distance or displacement, you can say. F of t is equal to k y of t f of s, its Laplace transform, it's a linear function, you will get k into y of s, no derivative. Here you have no derivative. For the spring, this is the relation you will use in the modeling, and for the torque and theta, you get tau is equal to k theta. You apply the torque, you get rotation. So tau is directly proportional to theta, tau is equal to k theta, tau of s is equal to k theta s. Here it will be s. This is an error. There are some errors, so just a simple one you should be able to understand now. Okay, now viscous friction, that is another important parameter which is used in the modeling, like we model it as a damper. Okay, so here the relationship is this: force is equal to capital D, that is the viscous coefficient, into dy by dt, derivative of y. So if we have derivative, what will be its Laplace transform? Please tell, you tell. I want to take the Laplace transform of this. Yes, ds, there will be multiplication with s and y of s. Okay, it will be ds capital Y of s. Okay, ds capital Y of s. Got? For the derivative, we multiplied with s, and there is also another term minus initial condition. Okay, but we have ignored it. We have taken it as 0 here. Okay, it will make things very, very complex if we have taken some initial condition into account. Okay, so if we take the integration, for example, if there was a relationship where here was I have the integration, so what will be the relation for the integration? What would be the no, just you need to solve the integration of y of t. Like if you have for example, if you have a function like this, f of t is equal to d into integration of y of t, then f of s will be equal to d capital Y of s. Now s, is it multiplied or divided? Yes, integration, for the integration, yes, it will be divided. Okay, good. So let me clean the whiteboard. Okay, now here for the rotational torque, we have the viscous friction tau is equal to d theta over dt. Similarly, tau of s will be equal to ds into theta of s. Okay, so now motion's second law is summation of all the forces is equal to m d2y over dt square. So this is another different approach which is from the Norman's nice book. He uses things differently, but the answer is same. So I will tell you the difference accordingly. Okay, so summation of all forces is equal to m into d2y over dt square. That is the Newton's law. Okay, and its Laplace will be m summation of all forces f of s will be equal to m s square into y of s. Okay, now here summation of all torques is equal to j2 d2 theta over dt square, the same in the rotational form. Okay, m is replaced with the j, that is the, this is the linear mass and this is the rotational mass. Okay, and summation of all forces, rotational forces, which are torque, is equal to j s square theta s. What? Okay, now j is the moment of inertia or the rotational mass. Okay, so far so good. So degrees of freedom, what are the degrees of freedom, or DOF? Degrees of freedom are basically the independent motion, like x and y are two independent variables. So if you have a system in which you have two independent variables to describe the system x and y, you have 2 degrees of freedom. And if you need 3 independent variables like x, y, z, you will have 3 degrees of freedom. So linearly independent points of motion in a system, a point of motion can move while others are still. So that point will be independent of all other points. Okay, so this is the independence, the number of independent variables in a system, you can say it degree of freedom. So now analysis of mechanical system, we want to analyze the mechanical system. So identify the degrees of freedom, points of motion, draw the free body diagram. What is free body diagram? We will draw a diagram and we will make the direction of the forces. Okay, we will make the direction of forces, whether the forces is towards left or right or upward or downward. Okay, and then we will add up all the forces and equate it equal to like Newton law. We will apply these laws according to the nodes approach. Okay, so for each FBD free body diagram, FBD means free body diagram, hold all other points still and sum the forces acting on the body while its motion set equal to mass into acceleration. Okay, we will do this. Now for example, you have this system, you have a mass, you have a spring and you have a damper. Now you are applying force F in, you are applying this force. So according to Newton law, you can see that when you apply the force, the F is towards right. Now make the free body diagram. This is the free body, the force F in is towards right, but spring, the force from the spring will be towards left, on the opposite. It will oppose the F in. Okay, so it will be Ky of S, Ky according to the Hooke's law. Okay, and this will be the ds into y of s. Okay, we discussed this earlier in the here we discussed these here we discussed this like Hooke's law we discussed here, and damping friction. Okay, so these are being used here. So summation of all forces is equal to m square s into y of s, that is a Newton's law. So summation of all forces will be equal to F in minus ds y of s minus k into y of s equal to ms square into y of s. Okay, so that is equal to, you can see that F in minus Ky of s minus ds y of s equal to ms square y. This is the Newton law equation, and take these towards right. So it will be F in s is equal to ms square plus ds plus k comma common y of s. We took this y of s common, so you can find the transfer function. Like transfer function will be output over input, that will be y of s output over input. F in s is equal to 1 over m s square ds plus k. Is it clear? It's very simple. Take this here and take this here. Okay, so this is 1 over ms square plus ds plus k. So here just we have applied the Newton law. Okay, there is another very simple way of solving such questions. Like if you have this mass, just make sum all like ms square plus ds plus k equal to force. Just do this. Okay, I will tell this ahead. I will tell this thing ahead. So first we will go step by step. Okay, now this question here, you have two masses, mass of 1 kilogram and mass of 2 kilogram, and here you have spring of 1 damper and 1 coefficient, and you have two distances y1 and y2. And where is the force? Here is the force F in. Now first make free body diagram of 1 and then make free body diagram of 2. Then you will have two equations with variables y1 and y2. Then you apply the Cramer rule and you will get the transfer function whichever you want. You want the transfer function y2 over f in. Okay, y2 over f in. So first make am I going okay or too fast? Is it okay? Okay. Yes. Now we start with the mass one. We have the force F in towards right, and this force will be towards left. Okay, opposing force, it will be towards left, that is y1s, and all these forces again, these will be opposite. These will be opposing the force F in. So it yes. Yes. Okay, so how will you write these two forces? Do we write this like 1 into y1 minus y2, because y1 and y2 are in relative motion here. So you will write 1 dot y1 minus y2. There are two motions involved here, not one. Okay, so you will write 1 dot y1 minus y2, and here you will write that s into 1 dot y1 minus y2. Okay, like this, 1 dot s into y1 s minus s into y2. Take this s common, you will get y1 minus y2. So now apply the Newton law, that is summation of all forces is equal to mass into m dot s square dot y1. Okay, m is 1 dot s square dot y1s. Okay, y1s, summation of all forces. So the summation of all forces will be F-I-N-S minus this and minus this. Okay, minus this, minus 1 dot 1, and then minus this, okay, and minus this is equal to s square y1s. Now simplify it, further solve it, you will get like this term, like y1 take it common and simplify s square plus s plus 2 minus y2 s plus 1 is equal to f in s. Now this is the final. Should I solve it to make this expression, or is it doable? Yes, is it understand? Okay, yes, I explain it. It's very, wait, yes, here. Okay, so what is it? Yes, it's basically f in minus 1 dot y1 minus 1 dot y1, it's basically y1. Okay, and minus y1 plus y2 minus s y1 plus s y2 equal to s square y1. So f in is equal to minus y1 and minus y1, it will be minus 2 y1 and y2, here it is y2 and here is s. Wait, it is minus 2 y1, it is also here minus s y1, make the y1 close. Okay, then we have y2 plus s into y2 is equal to s square y1. Okay, also take, you can also take this y1 here, so it will become minus s square y1 minus 2 y1 minus s y1 plus y2 plus s y2 is equal to minus f in, or you multiply it with minus, you will get s square y1 plus y1 2 y1 plus s y1 minus y2 minus s y2 equal to f n. Okay, here. Okay. So now take y1 common, it will be s square plus 2 plus s. Okay, s square plus s plus 2 or s square plus 2 same thing. Okay, also take minus y2 here common, then it will be 1 plus s. Okay, and it is equal to f in. So you can see that this is the expression you get. Okay, yes. So it's basically it needs practice, you have to do a lot of practice so that you come at this level, because without practice you won't be able to even solve this equation correctly. You will do many mistakes like plus minus, you will make a very horrible equation here, and that will definitely your question will make your question wrong. Okay, so this is how you got the free body equation for this. Similarly, you can get the free body equation for the 2. How we will get it? Here you can see that for the 2 there is no force applied on it. Okay, but this force, what will be its direction? It's will be direction. It's, you can see that its direction, it's towards left. Why left? Why is it left? Because you are pushing it towards this, towards right. So this spring will make its force towards left. Okay, it cannot make its force towards right, because if it makes its position, its force towards right, it will pull 2, which is not possible. 2 will not be pulled, it will be pushed by 1. Okay, you got my point? So therefore you have here 1 dot y2. Okay, now similarly this will again oppose it, this spring will oppose its motion towards right, therefore this will be also towards left, that is one dot. That the direction is tricky here, the direction, setting the direction is tricky. So there is very easy method to solve this question, which I will explain later. Very easy piece of cake. So with no kind of any doubt, with no kind of any error, I will tell you later. So this is one dot, this will be one dot, your simple one, and this one dot y2. Wait, now here there will be relative motion, you will now you will write y2 minus y1. Okay, one dot y2 minus y1, and here you will write that one dot s dot y2 minus y1. Okay, so you can see that one dot y2 minus 1 dot. Now just you can see that now how you will add these things. Summation of all forces is equal to summation of all the forces is equal to mass m, which is 2 dot s square dot y2. Okay, so this is the first equation, summation of all Newton law, that is Newton law. And now sum all these forces which are towards left. You here you are modeling like you are making the force towards right as positive, and you are taking the forces towards left are negative, so therefore take these as negative. So minus of y2 minus y1 minus s into y2 minus i1, and similarly minus y2 is equal to 2 dot s square is equal to y2s. So solve it and you will get expression like this. So should I need to solve it, or is it okay? You will get okay. Okay, so you have minus y1 into s plus 1 plus y2 into 2s square plus s plus 2 is equal to 0. Now apply the Cramer rule. Now just which on the very first lecture I started with this thing, because I knew that these things will be used. So you have these two equations, y1 y2, you have two variables, so you need two equations. So you have 1 and 2, so make a coefficient matrix that will be s square plus s plus 2 minus s plus 1 minus s plus 1, 2s square plus s plus 2 is equal to y1 y2, and then you have f1 and 0. So this is the model of your system. This is the model of this system. Have you used Matlab software? Yes, let me tell you something. Yes, let me tell you something. In the Matlab, the meaning of Matlab, what is the meaning of Matlab? No, the word Matlab, what is the meaning of Matlab? It's matrix laboratory. Matrix laboratory. So in the Matlab, what is actually happening in the Simulink, for example? In the Simulink, this thing is running. These equations are basically running in your Matlab. So when you model something, basically these equations are actually running behind your software. So control system is about 60 to 70% matrices. It is about matrices. So this is you got the matrix form. Now what do you need? You need the transfer function y2 over f. y2 over f. So you need y2. Here where is y2? This is y2. So how will you get y2? Just make this column f1 and put it here and determine delta or a2, and then also determine the whole determinant and divide it, you get y2, like Cramer rule. Remember? This is how you make it. If you take its determinant, if you take its determinant, this multiplied by this and minus this multiplied by this, so if you solve you will get expression like this. Okay, and for the a2, how will you get a2? Replace the second column with this. So here f in 0, here 0 and 0 minus into minus s plus 1 into f, so it will become plus f in into 1 plus s, like this. Okay, got it? How did you obtain this? Tell me. A2. Yes. Hmm. Yes, yes. Here it is 0, so it will be 0. S plus 1 into Fn. Okay, you get this. Clear? Very easy. Now just divide these two, you will get your transfer function. Okay. And when you f in, you have f in here, make it here, make it below here. Okay, so you got your answer. This is your answer. S plus 1 over s square plus s plus 2 into 2s square plus s plus 2 minus s plus 1 whole square. You can simplify it further, but it is not needed. It's not needed. You just need this equation. If you are able to get this equation, for example, if you want to further check the stability, you can further simplify it, make it equal to 0, apply the Ruth Horvitz criterion. We will discuss later it in chapter 6. For the stability chapter, we will discuss this, and we will then able to decide that whether the system is stable or not. Now please look at these matrices. I just want you to look at these matrices. It's very piece of cake. It's very easy. How? So just see this. Here on the mass 1, how much components you have connected? 1 2 3. Okay, 2 springs, just add these, it will be 2. 1 plus 1 is 2. Okay, and you have one damper here, so it will be 2 plus 1s, and mass is 1, so you have s square, 1 dot s square, that is s square plus see it here, s square okay, s square plus s from where this has from this stepper, and plus 2, where 2, because 1 plus 1 equal to 2. Okay, so sum of all the components, sum of all the impedances connected to mass 1. Okay, this is 1 1, this is 1 1 and matrix, and this is 1 first row second column 1 2, and this is 2 1 2 1, and this is 2 2. Okay, you remember this is basics. Okay, now see this, see this, just minus, apply a minus negative, then add all the components which are in between 1 and 2. So these are 1 s, that is s plus 1. Okay, you have minus and s plus 1. Okay, now come here, apply the negative and add all the components between 1 and 2 which are same, that is s plus 1. Okay, now for the 2 2, sum all the components which are connected only to 2. So here are 3 components like previous one you have, but the mass is 2, so it will be 2 dot s square. Okay, so you have 2s square plus s due to one damper, and plus 2 due to the both springs. Yes. Okay, then write f y1 and y2, the two forces y1 and y2, and then here you have the force, external force, which is only applied to the mass 1. So write its Laplace here, fi in, and there is no force on 2. Okay, so write 0 here. Similarly, in electric circuit, we will model this force with the voltage source. Okay, so we will write the voltage where there will be a DC battery connected, and 0 where is no source present. So is it matrix form clear to you? Yes, it's very easy. It's a piece of cake. Just add all the components, the Laplace of all the components which are connected to the mass 1, and here you have minus, then add all between 1 and 2. And for example, if we have another one, third, so here you will having a 3 by 3 matrix. Okay, you would be having a 3 by 3, let me delete it, like a, yes, you would be having this is 1 1 1 2 and 1 3. You will be having minus sum of all the components between 1 and 2, and then minus sum of all the components between 1 and 3. Okay, similarly you will be having here 2 1 2 2 2 3, and here 3 1 3 2 and 3 3. Okay, here all everywhere negative, only this one positive, the 1 1 2 2 and 3 3. So this is for the big system where you have the 3 energy storage element, or you have third derivative of differential equation. So here what is the order of differential equation? Here for this system you have second order system. This is a second order system. You would be having a second order differential equation here. Okay. So now should I move forward? Okay. I think, is it clear to you now? Yes, exactly. Okay, now come to the second question. So I will also solve this step by step. For the first with the free body diagram like this, and then we will see this from the matrix form, which I told now. Okay, now here what is this? Yes, it's damper. And what is this? Yes, this is the mass, and this is the y1 displacement towards right, and this is spring, and this is a force, and this is x2. Here you have x2, but for the x2 you don't have any mass here. Okay, you just have a spring here. Okay, but you have x1 and x2, two displacements. So first make the free body diagram of 5. So 5, so it's force direction of force. Again you can see that there is no force directly on 5. Force is on the spring, it's not on 5. So the damper force will be towards left. You can see that the damper force towards left. So it will be, you can say that s dot it will be s dot y. No, it's what is this? This is 4. Is it 4? Yes, it's 4. It's confusing. It's I think it's 4. Yes, it's 4. You can see that minus s into x1. It's 4. 4 dot s into x1. Okay, x1. Okay, and then second force is like the spring force, which will again be opposite, because if the force acts like this, its force will be opposite. Yes. Okay, so it will be 5 into x1 minus x2, x1 minus x2. Okay, so it will be minus 4x1 minus 5 into x1 minus x2 equal to 5 dot s dot x1 square. Sorry, 5 dot s square dot x1, Newton law. This is Newton law. 5 dot s square x1 is equal to these summation of all forces. We take the forces towards left as negative and towards right as positive. Now write the equation for this mass. Here there is no mass, so you will be having 0 dot s square dot x2. Okay, there will be 0 dot x2. Okay, so here you can see that 0 dot s square dot x2. Okay, it is equal to sum of forces. So sum of forces will be F in towards right, but that will be opposite. The spring force will be opposite. So it will be 5 into x2 minus x1. You can see 5 into x2 minus x1, but it will be negative. So minus, it will be F in minus 5 x2 minus x1 equal to 0. Why 0? Because there is no mass here. Okay, so this is equation now. Your equation 5x2 F in minus 5 into x2 minus x1. It's very notes are very here. It's minus f minus 5 into x2 minus x1 equal to 0 dot s square, that is 0. So now you can draw the equation. If you draw the matrices, you can clearly see. Just make let's make the matrices form. So add up, first of all, add up all the forces here, which are 5 s square plus 4s plus spring 5, and minus between these two is only spring. So here you can write only minus 5, and here you can write only minus 5, and here there is no mass and there is no damper, but there is only spring. So you have 5 here. It is equal to your, here you can, sorry, here you have it's difficult, x1 x2. Okay, and now where is the force? It's on the 2, it's not on the 1. So for fun it is 0, and here you will write as f in. Okay, that is the transform. Yes, if you solve these two equations, you will get exactly the same equations. Okay, you will get the same, exactly the same equations you will get, which are you are getting here. Okay, is it clear? Clear? You can see that minus 5x1 plus x2 is equal to f in, this same equation. And if you multiply this like s square plus 4s plus 5 into x1 minus 5 is x2 equal to 0, you will get the same thing. Should I solve it? Matrix form. Yes, 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 yes. I will also solve some questions from the book of Norman S. Nice. It's very easy. Okay. Now same conditions apply here for the rotational, but we will go step by step. For example, here you have the rotational system torque in theta 1, and then you have the rotational mass 1, again spring and damper, and 1 1. So summation of all the torques is equal to j s square theta. Here what is j? It is the rotational mass, the same Newton law. Okay, it is the same Newton law. So theta in minus 1 dot theta in minus 1 dot theta 1 minus theta 2. What is this? This is spring. Okay, 1 dot theta 1 minus theta 2 minus 1 dot s into theta 1 minus theta 2. What is this? It is the damper. Okay, it is in between theta 1 and theta 2. Okay, that's why we are taking theta 1 minus theta 2. It is equal to 1 dot s square dot theta 1. Okay, the Newton law equation. So you can now rearrange it, take these two terms towards right. You will be having 1.5 you will be having s square theta 1, and then solve it and then you will get theta 1 into s square plus s plus 1 into minus theta 2 s plus 1 is equal to tau in. Again you can see that it's very clear that yes, you can say theta 1, just add all the impedances connected to 1. You can see there is s square plus 1 damper s plus 1, and then minus uh, minus the sum of all the impedances between 1 and 2, which are s plus 1. Okay, here you can see that s plus 1 and minus the, and the torque is applying on 1, therefore equal to tau n. We will, if we make in matrix form, we will get very simple like this coefficient matrix and then theta 1 and theta 2 matrix. So for the theta 2 point, no, for the theta 2 point we discuss it minus 1 dot theta 2. What is this? This is this minus 1 dot theta 2. Okay, it is connected to the this static body, yes, like a wall static body, minus 1 point s theta 2. Here you can see 1 point theta 2, because these are on the right side, these have no links with the in between theta 1 theta 2. Now for these two terms we will write as like here minus 1 dot theta 2 minus theta 1. This is for this spring, and minus 1 dot s theta 2 minus theta 1. Okay, and there is no force, so equate it equal to 0. There is no torque here. Okay, so now solve it. If you solve these things, you get expression like this. Okay, again see this, please, minus theta 1, there is minus, and add all the impedances between theta 1 theta 2, which are basically 1 1 and this 1 plus 1 and plus theta 2. For the theta 2 damper you have connected this and into this 1 plus 1, yes, 1 plus 1, and that is your sorry, 2 dampers, 2s and 2 springs, so you have 2s plus 2. So here you will be getting theta 2 over theta this is your transfer function which you want, which you get you can get easily from here. Actually I am seeing there is some error. You have to tell what is the error here. This theta 1 you can see that this theta 1, it should be according to me, it should be here. It's like here, because in between there also comes the mass, so we are not taking the mass in between. Okay, you can see that we are not in here, it should be like here. Okay, it should be like here. Maybe we have to see this in the book. Okay, so did you get my point? For the rotational system, the law is the same as for the linear systems. Okay, we discuss it further. Provide the mechanical advantage and okay, torque for rotational speed. Okay, now this formula we discussed in the first chapter, like T2 over T1 is equal to theta 1 over theta 2 is equal to N2 over N1. You must have to have this thing in mind. Where you have greater number of teeth, you will have greater diameter. You will have R2 over R1, directly proportional. Okay, greater number of teeth, greater torque, but speed will be inverse. Okay, so therefore you have theta 1 over theta 2, or equal to where you have greater number of teeth, you will have less RPM. Okay, less rotation, and where you have less number of teeth, you will have greater RPM and less torque. Okay, now see, please see this system. This is a shaft with N1 teeth, and this is a shaft with N2 teeth. It is connected with the J, and there you have a K spring and a damper D. Okay, now your objective is to find theta 1 over T1, theta 1 over T1. So one thing is that you reflect all the impedances towards right and solve the question, or you reflect all the impedances towards left and solve this question. And one thing to remember is this: if you reflect T1 here, okay, if you reflect T1 here, you will yes, here is the book. You can see this diagram here. Okay, T1, theta 1, N1, R1. Okay, R2, its radius, N2, theta 2, and T2. Okay, it will move towards clockwise and it will move towards anti-clockwise. Okay, so here you have theta 2 over theta 1 is equal to R1 over R2 is equal to N1 over N2. So these are inversely, theta 2 and R are inversely proportional. These two are directly proportional, and theta is inversely proportional to both. So ta1 theta 1 is equal to T2 theta 2. It is basically the power, input power. P is equal to T theta. It is the power. Rotational power, it remains constant. So T theta 1 is equal to T theta 2, T2 over T1, theta 1 over theta 2 is equal to N2 over N1. And this is like if you reflect this torque and theta towards right, what you need is just multiply with N2 over N1. Destination teeth over N1 into T1, N2 over N1 into T1. Okay, N2 over N1 into no scare. Just the thing is, there is no scare involved here. You are moving your torque. Okay, that is important. And you will be having here theta 2. So if you want here theta 1, just write it as N1 over, just write this, like if you want to get theta 2, what you have to do, you have just write it here theta 1, you have to N1 over N2 into theta 1, opposite of this, N1 over N2. Okay, N1 over N2 into theta 1. So you will be having here N1 over N2 into theta 1. So okay, if the other thing is, if you reflect all the J, D and K towards left, if you reflect it towards left, what you will do is destination shaft, that is N1 over N2 whole square into J plus N1 over N2 whole square into D plus N1 over N2 whole square into K. Okay, J N1 over N2 whole square plus D into N1. It's the destination shaft here. Okay, N1 is the destination shaft. Okay, you have to make square for the j, d and k. Please remember this thing, j, d and k. But if you want to shift only torque or theta, you just need to multiply with the gear ratio. For this one, like torque, you just need to have n2 over n1, same as this, destination shaft over source shaft. But for the theta 2, you have to make it inverse, because these are inversely proportional. Okay. Okay, so here you can see, now I open your notes here, you can see it clearly. Okay, so here theta 1, tau 1, n1, here it is theta 2, tau 2, n2, k, d. Okay, so here you have free body diagram. If you make the free body diagram here, you will be getting this force, that is k theta 2. Okay, k theta 2 towards opposite. If you make it down, if it is in the down, and it's basically posing this force. Okay, it's posing this force. Like if you want to rotate it like this, it will oppose it opposite. Okay, so you will having k theta 2. That is where sometimes it makes it difficult for the free body diagram, because it's a mechanical thing, and if you have mechanical background it will be easy, but if you don't have any mechanical background you can make mistakes. So the easy thing is the matrix form, which I told you earlier, which is very simple thing. Okay, so k theta 2, and it is it will be your d theta 2, it will be your downwards d theta 2. Here you will be having ds, basically you would be needing ds theta 2. Here you have ds theta 2, and here you have theta 2 upwards and torque 2 upwards. Okay, torque 2 upwards. Okay, torque 2 is equal to theta 1 over theta 2 is equal to n2 over n1. So theta 2 is equal to n1 over n2 is equal to theta 1, and torque 2 is n2 over n1 is equal to d1. So just see what you have to find. You have to find theta 1 over t1, but here you have tau 2 and theta 2. So you have to accordingly convert your theta 2 into theta 1. So you have equation like t2 minus ds theta 2 minus k theta 2 is equal to js square theta 2. That is the Newton's law. Okay, Newton's law. Torque upward force is positive and minus downward force, that is minus ds. This is not 2, this is s. Here this is error, this is s. Why s? Please tell me why s. Why ds? Yes, this is damper. So you have, you should be sure, you should not doubt yourself. Okay, you must be sure. Please tell with surety, don't doubt yourself. It's very important. Yes, it's ds because of the damper. Okay, and this is the Newton law. Sum of all the forces is equal to js square theta 2. Why s square here? Why s square? Why s square? Because of the two what errors. When we get s square in the Newton's law, F is equal to ma, and a is equal to d2x over dt square, right? You have double derivative, so that's why you are getting s square. Okay, so here t2 minus ds theta 2 minus k theta 2 is equal to js square theta 2. So shift these towards right and take this theta 2 as common. You have ds js square plus ds plus k into theta 2 is equal to t2, and now make point here conversion. Theta 2 is equal to n1 over n2 is equal to theta 1, and t2 is equal to n2 over n1 t1. Yes. Now just find theta 1 over t1. Okay, that's your question. It will be very easy, and you can see that n1 will become square. It will be, when you cross multiply, it will be square. So it will become same like j into n1 over n2 whole square plus s square plus d n1 over 2 whole square s plus k into n2 whole square into theta 1 is equal to tau 1. So the transfer function will be theta 1 over tau 1 is equal to it will be equal to this j into n1 reflected j, reflected d and reflected k. Simple. You just reflect these things towards left and then apply the simple theorem. I will make it very simple ahead, don't worry. Okay, so j into n1 over n2 whole square. N1, where, what is the n1? If n1 is above, so where we are moving? Are we moving towards left or towards right? Yes. No, if we move towards left, what will be the destination shaft? Will be n1. It will be n1. Okay, so destination is n1, n1 over n2 whole square. If we are moving from right to left, if we move from left to right, what will be the destination? N2. Yes, then will be n2 over n1 whole square. It will depend on our question where we are basically moving. Are we moving towards right or we moving towards left? Okay, I show you from the formula here. Here is the formula. Number of teeth of the gear on destination shaft over number of teeth of the gear on the source shaft, and then it's square. Square for the d, j, d and k. Okay, for the j, d and k. But for the torque and theta, we just need to multiply with the gear ratio, just n1 over n2 or n2 over n1. Okay. Okay. So this is this we completed this thing. Okay. Now we are moving further. Yeah. Okay, as you wish, so we will stop here and we will discuss further in the next lecture. So okay, so thank you very much. I am stopping the recording. Thank you very much for listening.